there.
Yeah, it's fine.
It's fine. It's fine.
Good.
Excellent. So, welcome to our research seminar series. Immense pleasure to have. I never quite know. Do I go with official name?
No,
Masoumeh Mansouri.
I will go for Iran.
Iran here, guy who is now an assistant professor at the School of Computer Science at the University of Birmingham. He was previously at the University of Örebro, did their PhD there. I've forgotten what it is actually. I need to read this out, right? Okay. Investigated a meta-constraint-based reasoning approach for hybrid reasoning in robotics.
Oh, yes, I did.
Yes, you did, just so you know. So that was the work previously done, and I think you've been here before, maybe in 2019. So,
sometime.
And it's also, you know, good to see her going to University of Birmingham, where I spend a bit of time, so I know what she's up to from that perspective. Yeah, I don't want to talk too much about it. I'll let you crack on, talking about combining task and motion planning, challenges and guidelines. I'm looking for the guidelines. I'm aware of the challenges.
Oh, wow. Yeah, I should have more thinking on the title. Anyway, thank you so much for inviting me, Mark. I had a great time last night and now, and it's been great to be here. And thank you so much for actually coming in person. I know actually everyone from YouTube, so it's already I feel very close to this lab. So I assume that everyone is a kind of roboticism one way or another. That's a good assumption for them. Yeah, right.
I'm not. I'm sorry. It's fine. You took the robotics. I'll follow along and I'll ask any questions.
Right. Yeah. Sure. That's okay. Good. So yeah, I'm going to talk about combined task and motion planning, and I will start a little bit more general than that because my research is on hybrid planning, and the combined task and motion planning is an instance of that. That's my small research group, my fantastic PhD student postdoc, and the name of my lab, Hybrid Planning for AI and Robotics. I'm a roboticist, one might say a fake roboticist because I have a computer science background. I also do another type of research, which I'm not going to talk about it today, but I'm extremely passionate about that. I'm leading a network on critical culture and robotics, in case you're interested in this kind of stuff. Yeah, please go and check out and approach me. Please check out my publication. You will see what's about. It's about critical culture robotics rather than the cultural robotic as such. But I'm not going to talk about that. I'm going to talk about hybrid planning, and more specifically, combined task and motion planning. What is hybrid planning? Sorry for those of you knowing these things quite in depth, but I will give a really brief explanation. So very much do planning, meaning that devising an algorithm that come up with the sequence of task or motion or movement for a robot. We usually have to represent the environment. In the task level, if I want to go from here to your lab, I'm thinking in my head, I'm getting out of this building, turn right, go, I don't know, take a road and then go to the building, go to the elevator. But if I'm a robot, in addition to that, I have to come up with the sequence of motion, how much force I would devise to walk, how I open the door, and all those details, which we call it normally motion planning. And there are different representations for that. Usually for the task planning, we have a strict abstract representation, and for the motion planning, we have differential equations, basically, representing aerodynamic, kinematic constraints. And in order to make the plan of me and the robot going to your lab, I have to combine these two. That combination could happen in a lot of ways. For example, you come up with this high-level plan, and then you refine it in the as a motion plan. But sometimes it's not possible to do it, hierarchical. You have to do it at the same time. And I'm interested in one of those applications when you have to do it at the same time, because the hierarchical way is not challenging enough. So hybrid planning has a lot of application. If you're doing robotics, and why this application is put it here. This is the stuff that I did. So of course there are more applications for hybrid planning. And why I'm talking about hybrid planning and not necessarily task and motion planning, because we have temporal planning, we have spatial planning, we have geometrical planning, basically reasoning about action, considering different types of knowledge and combine them together. That's hybrid planning. But more specifically in this presentation, I'm talking about combined task and motion planning. So that's the paper we wrote in 2021, Combined Task and Motion Planning Challenging and Guidelines. If you are doing this type of research, I do encourage you to read the paper because I wrote the guidelines there. And yeah, but I'm going to talk about slightly about this paper today, not in depth. So the challenges, which Mark doesn't like to hear, but I'm going to tell anyway. So most people when thinking about solving the task and motion planning problem, they look at the application, but they have to think about certain specific part of application. And what are those specific aspects? We wrote it as a kind of 5 questions. And I'm really actually happy whenever I nowadays I give a talk about a particular application, people ask me, oh, in your question you define in this paper which one you consider. So it's a real pleasure that we see that paper, the question we put it out there, has some impact in the community. Anyway, obviously you have to think about a different level of abstraction. Is this a problem only solved with the task planning domain? For example, if you're doing a game, probably you don't need to do kind of motion planning. And yeah, but what is the what level of abstraction we have? And if we have, for example, both symbolic model and continuous model, the way the example I just used, how we want to represent them? Are we using a graph, grid? What we're going to represent for the symbolic part? Are we going to use a PDF? Or what? That's the question. What's the continuous knowledge representation? So motion planning, for you are aware of that. You have, textbooks of motion planning, different approach, PRM, RRT, I don't know, spline-based motion planning. All of this, these are the ingredients we have, and which of the best for our problem. And the specifying best learning, of course, nowadays everyone wants to learn, but there are certain applications, especially with the industry, they don't want everything learned. They have a specific behavior-specific set of rules. We don't want to learn them, we want to specify them, but probably there are bits in our application we want to learn. Do we need online planning, or if we devise a offline planner and we can use them? In a lot of applications, it's impossible not to use online planning. And planning with uncertainty, of course, uncertainty it has different types of uncertainty in time, uncertainty and outcome of action, uncertainty in what we see, what the robot sees, and which of those uncertainties we can assume, which of them can assume that is is fixed. We don't. We have a complete knowledge. These are the questions, the ingredients, the question we have to think about before approaching a task and motion or hybrid planning problem. And I'm going to give you a couple of examples from my own work, and I try to address some of these examples and how I would answer them in particular application I've worked in the past. Strangely enough, the first project I'm going to talk about, I don't have any results because it's a project. It just started, and I would love to talk about the task and motion planning aspect of that. The problem is called Convince. The project called Convince, the European project, which I'm one of the PI on this project from University of Birmingham, and called Context Aware Verifiable Adaptive Dynamic Deliberation, which means nothing really. And what is this project about? Is to devise a cognitive deliberative system, which again to me means nothing. Not everything you do, guys, I'm sure is a cognitive deliberative system. But the specific about this project is to come up with a tool chain that is verifiable. So meaning that the tool chain, if you want to have a, you know, you want to set up an agriculture or a robot, instead of doing for picking up place, instead of doing everything from scratch, hopefully at the end of this project, there is a tool chain that you can specify for your application. And which that tool chain should guarantee the certain behavior with respect to a specification. If your specification is to pick up, I don't know, pick up strawberry in certain time, in certain fashion, you have to model it. And that tool chain hopefully have to be able to say, oh, your model is actually guaranteed to produce this behavior. But then you plug your robot doesn't do that. So there is a kind of a verification on the fly, or they call it monitor, the online verification, that's able to refine your model about the environment. And that tool chain plus the verification is the output of this project. And obviously, the interesting part of any robotic project is detecting unexpected situations. Because if you know everything from scratch, you put up in a model and you put up the contingency plan in advance. We can't know everything. And the question is how we detecting unexpected and do some sort of concrete analysis, and what would the explanation for that in order to incorporate for initial model. So this is the project is over the 3 use cases. The one use case is museum robot, basically 2. And our aim is to beat your museum robot. No, it's not. But probably we should. And this is one of the actually oldest robotic problems. Another oldest robotic problem I still want to solve is the robot vacuum cleaner. Because I'm an academic, I don't have actually a robot vacuum cleaner, but we was told that if you have a robot vacuum cleaner, you have to actually tidy up your apartment before you put the vacuum cleaner. They can't, they're still stuck in the socks or wire or something. And the project should able to solve those problems at the end of the project. And that this is also an assembly robot. Is the idea is to put up the deformable bricks on top of each other in collaboration with humans. And in all of these 3 applications, there's a task and motion planning part. The challenge is different though. So in the manipulation robot, in the assembly task, the task and motion planning really should be done at the same time, because the order in which you do assembly, it depends on the kinematic constraint your arm has. You cannot just come up with a sequence and then say, oh, okay, now you do your assembly, but probably the task you specify for the arm is actually not doable for the specific arm. So, and that's a good example of the task and motion planning. And this is the part I'm leading on the project, task and motion planning in dynamic environment. And by dynamic means everything could be human, could be the socks over the floor, which could be moved, and the reasoning about all those at the same time. Yeah. So, just one couple of more. I'll talk about this and then I move on, because this is a project I'm going. I don't have any results, so I can't show you cool videos and so now and look how amazing things that I've done. But already I have to ask a lot of questions that I asked all those questions that I put up there. So how the representation of uncertainty in all this application is different. We have human there. This uncertainty could be actually resulting of the partial observability, because one brick is just block the view for another village, and also the human moving around here. So the uncertainty over collaboration and intention of the human. Here the uncertainty would be the amount of socks or wire and the change and all the furniture. So the representation for the uncertainty is different. As I mentioned, the task and motion planning is more tight here rather than the other 2. So the symbolic representation also is different. For example, here we can represent an environment in a graph with a topology map where the interesting area are the artwork. But here for the coverage, I want to cover every area. Probably if you look at this floor, these are already in a grid. Perhaps I can use a grid representation. And obviously the constraint and the motion constraint of this robot are different, hence the motion planning I can use. So there is a lot of things going on. So, but why so this is a project I've done before, and this is a good example of why task and motion planning really should be solved at the same time. In the case of assembly robot, which is in the Convince project, also in this previous project, this robot is a robot in motion. This is an assembly task that there is a wiper motor. There is a basically there's a sequence of things has to be done. So you have to pick up a pin, put it there, and then you have to use another tool. I forgot the name of the tool. That's why I use pin. And so basically you have to use certain tools and items in certain order, and you have to do it quite in an efficient way. And is it a video? So, of course, if you use and the task is to allocate which, if you have dual arm robot, you have to allocate which arm does what. And you cannot just allocate randomly or use quite a task allocation method from AI, because again, we have the constraint of the arm. So not any AI algorithm off the shelf for task allocation would work. Also, there is a motion scheduling part here. Because we have a dual arm, we want to avoid arm collision. And we have so many items, so we want to solve it in optimal fashion. We don't want our one arm to really move a lot for another arm. So we want to do everything quite, in optimized way, as I said. We want to optimize the make span, the time to completion, and so the way I do that, I don't intend to explain the details of any of the work I present today. I want to explain that again here, we have to answer some of the questions I put it out there. Here, for the discretization and the symbolic for, I create RPO, my student with John, one of the former PhD students, create a PRM for discretizing environment, basically that symbolic approach. And then they use the constraint-based reasoning for the combination of task allocation and motion scheduling, where he represents time and the task constraint there. Yeah. So, yeah, this is enough. Again, here, as you probably noticed, there is no uncertainty handling. So we assume that we have knowledge of everything, and this is a structured environment, which is not necessarily the case in all of the assembly tasks. And even that is still the problem is difficult for the reason I just said. My favorite problem of all, I think you know this problem before, and I haven't given for the last 5 years any keynote talk or any sort that I haven't talked about this problem. It's just amazing. So, and I'm going to explain you why this is amazing. I have 2 active PhD students working in this project. And so, it's a mining application, but it gets more interesting. So these are the mining robots. They're huge mining robots. They're really huge. I've been in north of Sweden, and their wheels is as tall as me. Their job is going through this drill target, all those dots over there, and drill those drill targets. And when you drill, it creates a hole, and also a pipe. You know, when you drill, usually pipes scatter around the hole, right? And interesting, the task is basically how to an optimized way, the quickest way that these robots drill all the drill target. What kind of traditional computer science problem you can think now? The task is to go every node, basically. TSP, tablet expression problem. And so when you drill a hole, it creates a pile, and that pile becomes an obstacle for the robot itself and the other robot, because if you move over the pile, it defeats the whole purpose of the drilling, right? It puts back all these robots inside the hole. Why would you drill? Again, the perfect example of solving first-person problem. So you have to navigate this environment while you have to visit every node once. And why then this problem is so interesting that I keep still talking about it? Because if you get an off-the-shelf solver for a TSP, is out there. This is the most studied problem in mathematics and computer science. It doesn't produce a robot behavior that can work in this mind. Why? Because it can easily create a situation I did in drawing. This is my own drawing. It's not exactly precise because the robot is much bigger than the spacing of this pile, and the robot gets stuck between the piles that is created by its own or the other robot. So basically, the sequencing of the task restricted the motion. And this is a perfect example, a killer example of the combined task and motion planning. In this case, task is a sequencing of a drill target. And because you cannot just not thinking about your motion constraint, while doing planning, you cannot come up with this best TSP, getting a best TSP solver, and then call a motion planner to complete that. That doesn't work, simply. And yeah, I spent quite a lot of time on solving this problem practically, and what is called? In a theoretical way. So let's look at one of the practical video. This is my first result. As you see, it goes back. It actually goes back to 2015. Not the timing is wrong, but anyway. So what you see is I'm just stopping. What you see is the result of the behavior you see is the result of meta-constraint reasoning. The overall problem is divided to several sub-problems. Sequencing, and you see the result of this sequencing as this white arrow. Approach angle decision. Am I robot which approach angle I approach to the drill target, and that matters because these robots are non-holonomic, so you cannot just, you will see in the video, when you get maneuver, they will actually take a lot of the space for maneuvering, and that approach angle affects all the maneuvering. So also motion planning, which is shown by all this white polygon. Coordination, by coordination I mean robot-robot collision avoidance. Which robot task allocation, which robot does which hole, and sequencing within each robot. So all of this decision has to combine so that this kind of behavior produced. And okay, so I explained. So but also this is a showcase when you will see this robot in the middle of this region. It got broken and it has to take it away from the field. And yeah, I want to explain what's happening. Let's get into the interesting part. You will see, by the way, these robots are moving backward while drilling. These are not that exciting information, but it's going to get interesting. So the robot in the middle get broken, removed from the field, and the robot on the top basically take the mission is supposed to be the robot in the middle on his hand. And something interesting happened now. You will see this robot doesn't move. And you will see in a moment why, but I will tell you in an explanation. First of all, this green line is a virtual perimeter, which, for example, is there because there's a cliff, so the robot should not go beyond that. So the space which this robot has to move is very tight. And this robot is waiting because it's supposed to drill all this drill target. But if it didn't wait and it continued, all the piles that drilled by this machine would be destroyed by this machine because it needs all of those area to maneuver. So it's a very tight space, and you see, imagine it would continue, it would be destroyed by this machine. And you will see in a second that while this crazy maneuvering is done, the machine on the bottom starts moving. Yes, I mean, of course, this is not the most optimal solution. You would think that if this robot used that area for maneuvering, that would be less minimized time, which I did use this kind of reasoning in my second paper, which is in 2017 IROS, the one I actually put it up there, is a kind of a hierarchical optimization problem I use. So, yeah. So I'm not going to show you the video of the second video. Really, if you're interested, you can look at the slides. But here, we thought that, okay, if this is not a TSP, what it is then? So Sarah, a brilliant PhD student, started working on this, understanding the theoretical underpinning behind this problem. And she formulated that, she has devised a general algorithm, and she, for example, defined the self-deleting graph. I'm not going to explain this, but I just want to say, if we are interested to understand the problem in such a general way, and this problem is the same as, if you think about it, in painting, you have the same problem. If you want to paint an area, you don't want to go over the same place again. If you are doing an agricultural scenario, you don't want to go to a place that you are already in second application, already harvested because of the soil compaction. And you would think this problem is different, but essentially it's a kind of a dynamic coverage problem that the source of dynamicity is the robot itself. The robot moves and changes the environment. And of course, the difference is the discretization. In here, given the discretization, it was a drill target. In the case of painting and the harvesting scenario I just described, you have to kind of discretize the environment in one way or another. But essentially, the theoretical understanding of this variation of TSP would help us. Another problem, which is kind of a maybe not similar, but it's the same line of the things that we discussed today. This is the work I've done while I was in a research stay in Oxford. This is an application from Volvo Construction Equipment in Sweden. This is a very interesting problem. Again, theoretical, but with a clear application. And this is an inspired application scenario. So this robot, is a hauler, they're autonomous hauler, and the problem is how they have to allocate it to this crusher, gather some crushed stone, and dump it in unloading station. The problem is task allocation. Which robot has to go to which crusher in order to optimize the overall problem? Simple, right? The task allocation, you want to have an optimization criteria. You minimize the time. It's a really well-known problem in AI. And optimization, task allocation with the couple of the stations is really, really peanut. But why we did that, it is really peanut. There is an interesting constraint here. This crusher always produces gravel. It's like a tab, it never stops. And as a result, there has to be always a machine underneath gravel. And when it's full, it has to move, and there should be always a machine behind it, at least, to just replace. Right, so this is, if you don't respect this constraint, it would be very costly for Volvo, because it has to stop the overall system. They have to people on the ground removing all this gravel. So the constraint is a hard constraint. There always has to be a robot under the primary crusher. The secondary crusher, though, doesn't have that constraint because it's manual. If the robot goes there, you can manually put the stuff. So it would be interesting to see when the robot is finished with putting the stuff on this, and then you send another robot behind that. Again, is an interesting, about simple task allocation problem, right? Because if you have a time prediction perfect time prediction of how long does it take from this robot to move from here to here, then again you can solve a simple task allocation time constraint optimization problem. Again, why I'm doing this? Because the time is very uncertain. Because this robot moving in this environment, the robot dynamic is partially unknown. There would be a sandy patch, a robot may skid over. There would be, if robots when they're heavier, it goes slower than they're not. So we can't actually have a perfect time prediction. Hence, everything is much more difficult. How we solve this, I'm not going through the details. It's very, very high level. We look at the stochastic Petri net. We model the task allocation as a stochastic Petri net. A stochastic Petri net, it has different kinds of transitions. One was decision making, for example, which station we want to go, and there is a transition for capturing that stochasticity. A stochasticity which comes from uncertain time modeling, and we receive that uncertain time modeling from having a realistic type of simulation. We run a simulation and we learn basically that transition, and that theoretically this can translate it to Markov automata. This can be related to MDT. Well, everyone knows MDT, and then we have a team policy. Voila. I like this problem because you can actually theoretically guarantee over the specification you have. You could have learned this from data, but Volvo didn't have that data. In you guys, because you have a lot of collaboration with industry, they have loads of data. You can think of this similar application with similar constraint. You could have put your learn distribution. The video is not that interesting, because it's in simulation, and this work is actually accepted in each it's quite a prestigious area. However, from robotic point of view, I think the behavior is a bit conservative, and that's the price we pay, because it's very conservative, because you see there are two robots in the queue. Of course, this is a simulation, doesn't have a sandy patch or everything. It learns for those kind of environments. Well, yeah, you see that this R1 goes to actually primary crusher. Well, it could have gone to the secondary crusher in the perfect non-snowy environment. Okay, I'm not good with time. Let's see. Okay, actually very good with time because I don't have much slides. So here, again, there was some things I had to address in this application. What to learn, what to specify. I don't need to learn the allocation. I could have reasoned about this, but the learning part, it comes from I learned uncertain travel time. That's what bits I learned. The discretization wasn't that difficult because we have some, we could have, we had a graph, so it wasn't a problem. And again, here the motion plan also wasn't a massive problem. It has to only work for the kind of the vehicle we have. And because the policy, we have some sort of online planning, and uncertainty was a main driver. So that there was all of those things that we had to capture one way or another. Human error task allocation. I like this example. Is I did it with a master student of mine. It's cute. So it's not a massive result, but I like it. So you guys know this. You are one of the world experts of this thing, map of dynamic and environment modeling and everything. So the task is human error task allocation. It's so simple. Imagine a robot wants to deliver an object in an airport or in a shopping mall. So if there's a task A here, I have to deliver, and there's a task over there. And there's two robots. I'm closer to this, would be obviously goes to allocated to that. This robot is closer to that. Simple, right? Task allocation was again all this problem in AI. There is loads of amazing approach out there, action-based, is very effective. So what it does, it says that it's not effectively is a good, thing to always to allocate it to the closer, because probably we know that there's always, depending on the time of the day, there's always people passing by. So it's actually better to the robot allocated to the longer. It will be quicker if robot allocated to a further away target rather than the closer, because of the constant passing of the human. And this our human level task allocation, it actually consider that kind of area, that kind of problem. So we have Freeman, we use actually two types of dynamic math. So we use two different machine learning algorithms to model the human crowd, and we use action-based method using those learned models to perform actioning. And we show that it's better to look at the human crowd. The experiment is, I had the video, which I didn't put, sorry. And this is my last slide. It's, my PhD student who is about to defend, Joao, is one of the Iliad's project. I mean, he did an amazing job in looking at the old-fashioned control problem and solving the whole problem of task allocation, routing, and multi-robot coordination from the optimal control point of view. But the optimal control, if you have an experience with that, doesn't work in the multi-robot case, and doesn't work if you have a lot of obstacles, doesn't work if the robot is not holonomic. It's fantastic if you have two robots, probably, nothing more than that. But the solution you get out of that is totally feasible, because you incorporate dynamic pneumatic in the first place. So what he did, he basically used, for example, in one of his paper, used a kind of AI, old-fashioned AI network flow reduction. And the interesting thing about this is he has to discretize the environment. One of the important problems in robotics, which does usually overlook. We always assume that we have a graph, or we have a grid, or then we don't know how to discretize the environment. We don't put effort or I don't know, dedicate a couple of pages of our paper to a discretization. And he did discretize using Iris. Iris is developed by one of the PhD students at Tetros. If you know him, it's from MIT. They actually take those problems of discretization much more seriously than many other people. So you basically create a representation of environment of real space, and that would be the space that you're working on. You don't need to have constantly collision avoidance checking. The only collision that you have to take care of is the movement of another robot. He uses the network flow reduction to do some sort of high-level routing problem, and then he uses his optimal control method for for multiple robot to come up with the kilodynamically feasible path. Yeah, this is also simultaneous task assignment and motion planning and control and everything, but yeah, the video is not that exciting, unfortunately. I'm not going to explain this. I'm going to good practice and get some questions. So that's my summary slide. We have to, of course, analyze the type of uncertainty. And in some of the examples I showed today, the whole problem is built on the uncertainty. In some, we just totally disregard it because we could afford that. Determining the level of abstraction and what kind of representation we can use, like I discussed at lunch, the PDDL we have. So we have to say, okay, does this method, have the epistemological adequacy, what I want to represent or not? And we analyze carefully what we can learn Of course, it's much more charming that we have end-to-end learning, but end-to-end learning not necessarily works if you have combinatorial decision making in a robotic task, but we can actually learn bits of, search problem, like, heuristic. So if we can really locate where what we can learn, we can use the good old-fashioned AI technique like MDT or something, and devise a very good algorithm. Discretized problem. I think this is the problem overlooked usually, as I explained, and we had a lot of good algorithm AI, decade of half a century improvement on AI algorithms, work on the discrete search spaces, and we don't have all the discrete search space. How to discretize that is the important problem, because that's what is guide the method we're going to use for task and motion planning. And thanks to all my collaborators, PhD students, and wonderful colleagues. Thank you for joining. Also the people online, which are so many.
Hello, thank you very much.